Every physicist who has ever tried to explain what quantum mechanics actually says about reality has eventually arrived at the same confession. Not that the theory is difficult, not that it requires more study, that it is, at the deepest level, not understood. The most precise scientific theory in human history, confirmed to better than 1 part in a trillion, describes the behavior of every particle of matter in the universe, and no one agrees on what it means. Here is the result that makes them say this. Fire a single electron at a wall with 2 narrow openings. Do not watch which one it goes through. On the other side, a detector records where it lands. 1 electron, 1 dot. Do this thousands of times, patiently, 1 electron at a time, and the dots accumulate into a pattern. Not 2 piles, not the pattern you would get from any particle choosing one opening or the other, the interference pattern. Alternating bands of arrival and absence spreading across the detector in the precise mathematical signature of 2 wave sources occupying both openings simultaneously. 1 electron, 1 thing, 2 openings at once. Now place a detector at the openings to record which one the electron actually uses. The interference pattern vanishes completely. The moment information exists about which path the electron took, the electron stops taking both paths. 2 stripes appear instead of dozens. Remove the detector. The pattern returns. The universe behaves differently depending on whether it is being watched. That sentence has been confirmed in laboratory experiments thousands of times across 90 years with electrons, atoms and molecules large enough to see under a microscope. It is not a philosophical position. It is a measurement, and the word at the center of it, the word that contains the entire mystery, is a word so ordinary you've used it 10,000 times without once noticing what it might actually mean. The word is observation. Tonight we're going to sit with that word. We're going to pull it apart. We're going to find out what it requires, what it costs, and what it implies about the nature of reality when no one is performing it. And by the time we're done, that word will not mean the same thing it meant when you started. If this kind of slow, careful dismantling of things you thought you understood is what you need at the end of a day, I would be grateful if you subscribed. It helps this channel reach people who want exactly this kind of quiet. Now, let's begin. You already know what should happen. A ball thrown at a wall with 2 holes goes through one of them. It cannot go through both. It is a ball. It is one object in one place at one time. It travels through one opening, continues on the far side, and lands somewhere you could predict with a ruler and 50 minutes of arithmetic. If you fired thousands of balls at thousands of walls, you would get 2 piles, one behind each opening. Tidy, predictable, nothing to argue about. This is so obvious it barely feels like a claim about physics. It feels like a description of how things are. And for every object large enough to hold in your hand, it is exactly right. Now, replace the ball with light. In 1801, Thomas Young aimed a beam of sunlight at a card with 2 narrow slits cut close together and watched what appeared on a screen behind it. Newton had argued that light was made of particles, tiny corpuscles streaming in straight lines from every source. Under that model, 2 slits would produce 2 bright stripes on the screen. Clean, separate, exactly where you would expect. Young saw alternating bands, dozens of them, not 2. The light went everywhere it was forbidden to go. This pattern of reinforcing and cancelling bands spreading from 2 sources is what waves produce when they interfere with each other. Water waves do it. Sound waves do it. Young had just shown that light did it too. The conclusion was unavoidable. Light was a wave, not a stream of particles. Newton was wrong. The corpuscle theory was abandoned. Light moved into the wave column, and the category system that organized the world into particles and waves survived the update intact. For over a century, this was the settled picture. Atoms and molecules were particles. Light and sound were waves. The categories were crisp, well-defined, and backed by mountains of experimental evidence. In 1905, Einstein shattered the wave column. Studying a phenomenon called the photoelectric effect, he found that light hitting a metal surface would only dislodge electrons if the frequency of the light was above a certain threshold, regardless of how bright the beam was. An extremely bright beam of a low-frequency light could not knock a single electron loose. A very dim beam of high-frequency light could. This was incompatible with the wave picture. Waves carry energy spread continuously across their field. The brighter the wave, the more total energy, and therefore the more capability to dislodge electrons. But that was not what happened. The energy came in discrete packets. Einstein called them quanta. Each packet carried an amount of energy fixed by its frequency alone. If the frequency was too low, no single packet had enough energy, regardless of how many arrived. Light was a particle again, a photon, a countable, discrete, individual thing that delivered its energy all at once, like a tiny collision, wave and particle. Both confirmed by rigorous experiment, both correct, irreconcilable. Common sense is not wrong. It is a law written for objects you can hold. The categories that common sense relies on were built by evolution over hundreds of thousands of years of navigating a world of rocks, water, predators, and other people. They work perfectly at those scales. They were not built for electrons. They were not built for the scale where the categories themselves stop meaning what they say. And the experiment that revealed this most completely did not use light at all. Light having wave properties was, at least, explicable. Light was always slightly mysterious. It travels through empty space without any obvious medium. It had never fit cleanly into any category. The wave-particle duality of light was strange, but light was allowed to be strange. Then physicists fired electrons at the two-slit barrier. An electron is not mysterious. It was identified in 1897 by Joseph Thomson as a particle with a specific mass and a specific electric charge. You can fire electrons from heated wire, focus them with electric fields, count them individually as they arrive at a detector. Click, 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 discrete arrivals, one at a time. An electron is about as particle-like as anything gets. The interference pattern appeared. That result alone was alarming, but the experiment was refined to remove every possible alternative explanation. Physicists built equipment to fire electrons truly one at a time, each separated from the next by a long enough interval that no two could interact. Each electron leaves the source alone, travels alone, arrives alone. One electron, one dot. No shared wave, no mutual influence, no possibility of one electron interfering with another. Watch the screen over hours, over days. One dot appears, then another, then another. For a long time the dots look random. Then gradually, the structure becomes visible. Bands, not two piles, not the result of particles choosing one opening or the other. The interference pattern, emerging one electron at a time, from particles that each arrived individually, each produced one dot, each had no neighbours to interfere with. There is no other electron for it to interfere with. It is interfering with itself. That sentence requires a pause. One electron, one discrete, countable, individually fired thing. It arrives as a single dot, and yet the location of that dot, accumulated across thousands of trials, forms a pattern that is only possible if something went through both openings simultaneously. The pattern has gaps behind each individual slit, and concentrations in positions that the mathematics of two-slit interferent predicts exactly. No other mechanism produces this result. No other explanation is available. The electron was, in some sense, the language of classical physics has no word for, in two places at once. The question that writes itself is obvious. Which opening did it actually use? The obvious solution was to watch. Place a detector at the openings, something that registers which slit the electron passes through without blocking its path. A photon bounced off the electron at the critical moment, a change in an electric field, any gentle signal that answers the question without stopping the experiment. Let the electron continue, let the dot appear on the screen, and now you have both pieces of information, which opening it used and where it landed. Run the experiment. The pattern vanishes, not degraded, not slightly blurred. Gone. 2 stripes appear on the screen, one behind each slit, exactly as you would expect from particles choosing one opening or the other. The alternating bands, the mathematical signature of two-source interference, the result that required the electron to have been in 2 places, all of it disappears the instant a detector is running. Switch the detector off. The pattern returns. The detector does not disturb the electron. It answers a question, and the electron cannot survive being answered. This is the result that has not been explained in 90 years of trying, not because physicists gave up. Because every proposed mechanism turns out to be insufficient. The first and most natural explanation is physical disturbance. The detector needs to interact with the electron to register it. Any interaction transfers energy. Transferred energy changes the electron's trajectory. Changed trajectory, changed landing position. The interference pattern disappears not because the universe cares whether it is observed, but because the detector physically bumps the electron, and a bumped electron does not land where an undisturbed one would. This almost works. Werner Heisenberg formalized the essential idea in 1927. To measure position with sufficient precision requires an interaction energetic enough to scramble momentum. Precision in one quantity guaranteed imprecision in the other. Measurement disturbance was real, measurable, and physically grounded. Almost. In the 1990s, physicists built detectors that could register which slit an electron passed through while transferring the minimum amount of momentum that the laws of physics permit. They minimized the physical disturbance to the smallest conceivable value. The interference pattern still vanished completely. Then they went further. Marlon Scully and colleagues proposed the quantum eraser. Obtain which path information, then erase it before reading it. If physical disturbance were the mechanism, the damage would already be done. Erasing the record afterward cannot undo a bump that already happened. But when the which path information was erased, the interference pattern reappeared in the data. Not partially, fully. The pattern responded not to the physical interaction, it responded to whether information existed. So we need to look at that word more carefully. The word that appears in every description of this experiment. The word that seems to explain everything and actually explains nothing. Observation. What does observation actually require? In ordinary language, observation means a mind directing attention towards something. A person looking. An eye receiving light. A brain processing signals. This is not what quantum mechanics means by the word. In quantum mechanics, observation means any physical interaction that produces a record of a particle's state. A photon bouncing off an electron and continuing in a direction that encodes information about where the electron was. A detector registering the passage of a particle through a change in its own state. A correlation established between the particle's behavior and any other system in the universe. Consciousness is not required. A detector running in an empty room with no one watching produces the same result as one with a physicist in attendance. The question is not whether a mind is present. The question is whether information is present. If a record exists anywhere in the universe of which slit the electron used, the pattern is gone. If no record exists anywhere, the pattern forms. The universe is not responding to attention. It is responding to information, to the existence of a fact, and that is considerably stranger than a detector bumping an electron sideways. If you're still here, this channel was probably made for you. A quiet subscribe before we go deeper helps more people find their way here. Physicists built frameworks, not guesses. Mathematically complete, experimentally confirmed, precise enough to power the semiconductor industry, the GPS network, and the design of every atomic clock ever built. The frameworks work. The question of what they mean has been argued for a century without resolution. Every interpretation of quantum mechanics is correct about the data and silent about the reality. The first rung of the ladder is Copenhagen. Niels Bohr and Werner Heisenberg assembled it in the 1920s from the rubble of classical physics. Copenhagen says, the wave function is not a picture of where the particle is. It is a catalogue of probabilities for what you will find if you measure. Before measurement, there is no fact of the matter about which slit the electron used. The question has no answer. Not because the answer is hidden, because the answer does not exist. This feels manageable. It sounds like epistemic humility, like a theory admitting the limits of its knowledge. Use the wave function to make predictions, confirm predictions. Stop asking what reality is doing between measurements. Here is where Copenhagen falls. It makes measurement the defining event of the universe without defining what measurement is. When does the wave function collapse? What triggers it? Copenhagen says when a measurement occurs. But the theory does not say what counts as a measurement. The detector, the physicist reading it, the physicist's notebook, the room, the planet. There is a specific name for this failure, the cut, the boundary between the quantum system and the classical measuring apparatus. Copenhagen requires it but does not locate it. After a century, its location remains unspecified. So the ladder offers the second rung. Many worlds. Hugh Everett III, a doctoral student at Princeton in 1957, refused to accept the cut. He took the wave function seriously as a description of physical reality and applied it consistently to everything, including the measuring apparatus, the physicist, the room, the planet. In Everett's picture, the wave function never collapses. It branches. When the electron reaches the detector, two branches of the universal wave function form, one in which the electron went left, the detector registered left, the physicist read left. One in which the electron went right, and the same. Both branches are equally real. Both continue forward in time. This solves the measurement problem. No collapse, no cut, no undefined boundary. The mathematics runs cleanly all the way to macroscopic scale. No special role for observation. Here is where many worlds falls. It requires an unimaginably vast proliferation of parallel realities, branching from every quantum event that has ever occurred, inaccessible to any experiment, containing versions of every person, every particle, every measurement outcome simultaneously. Physicists who find this acceptable consider it a feature. The universe is as large as the mathematics requires. Physicists who do not consider it the most expensive solution in the history of science purchase the absence of a cut by multiplying reality infinitely. There is a third rung, pilot wave. David Bohm in 1952 proposed that particles are real and always have definite positions. The electron does go through exactly one slit, but alongside every particle travels a real physical wave, the pilot wave, that guides it. The pilot wave goes through both slits. It interferes with itself. It develops the pattern of amplitudes and nodes that the interference pattern traces. The particle follows the wave, guided to land where the wave is strongest. This explains the pattern without requiring the electron to be in two places. Deterministic. No randomness at the fundamental level. no collapse. Here is where pilot wave falls. The pilot wave must be a real physical field extending through all of space, sensitive to the configuration of the entire universe at every moment, and non-local in a specific technical sense. What happens at one slit can influence the pilot wave anywhere else instantaneously, not approximately, instantaneously. This sits in direct conflict with the spirit of relativity, though pilot wave theorists argue the non-locality cannot be used to transmit information, and therefore does not violate any measurable constraint. The ladder has 3 rungs. Each one reaches the next problem and stops. Sit with that for a moment. 3 complete mathematical frameworks, each developed by serious physicists, each confirmed by every experiment ever designed to test it. Not one of them agreed on what the electron was doing in the space between the slits and the screen. Not one of them has converted the others. Not one of them is universally accepted. Let's try to rescue the mechanical explanation one more time, because it contains something true, and that something true is worth understanding precisely before we accept that the real problem is stranger. To see where the electron is, you must touch it. To touch it, you must change it. This is not philosophy. It is geometry. To locate a particle with enough precision to say which of 2 slits it passed through, you need to bounce something off it, whose wavelength is smaller than the distance between the slits. A shorter wavelength means higher frequency. Higher frequency means higher energy. Higher energy photon hitting an electron means larger momentum transfer. Larger momentum transfer means larger disturbance. The arithmetic closes on you. There is no configuration of detector and electron in which the measurement is gentle enough to preserve the interference while precise enough to yield the path. Heisenberg's uncertainty principle is not a statement about clumsy instruments. It is a statement about the relationship between position and momentum at the level of quanta. The 2 quantities are conjugates. Measuring one with precision necessarily makes the other imprecise in a specific mathematical proportion. The product of their uncertainties is bounded below by Planck's constant. You cannot reduce it by building a better detector. It is a law, not a limitation. So the mechanical story is, detectors measure position. Measuring position disturbs momentum. Disturbed momentum destroys the interference. The pattern disappears not because the universe cares about being watched, but because the physical act of measuring has physical consequences. This is where the story should end. This is the flaw the mechanical explanation provides. The flaw is not there. Scully's quantum eraser proved it. The physical interaction still occurs. The electron still passes through the detector. The momentum transfer still happens. But when the witch path record is erased before anyone reads it, the interference pattern reassembles itself in the data corresponding to the erased events. The bump has already happened. The pattern returns anyway. The pattern is not responding to the bump. It is responding to the record. There is a name for what the pattern is responding to: information. The pattern disappears when a fact exists. Which path did the electron take? The pattern returns when that fact is destroyed. The universe, at the quantum level, appears to be sensitive to the existence of facts, not to forces, not to energies, to facts. If that is what observation means, then observation is not a physical act. It is a logical condition. And the question of what reality is between observations is not a question about measurement equipment. It is a question about what exists when no facts yet exist to describe it. We have covered a lot of ground. Take a breath before we go further. Imagine the electron leaving the source. No detector is running. No record is being made anywhere in the apparatus. The barrier with its 2 slits sits ahead. The screen waits further on. The electron is in some sense travelling. Where is it? Not somewhere specific. Not secretly in one location that we fail to know. The mathematics of quantum mechanics, applied consistently, gives a precise answer. The electron is described by a wave function. The wave function is not a picture of where the electron is. It is a description of where the electron could be found if you looked, and the probability of each possible location if you do. It spreads from the source outward. It reaches both slits. It passes through both simultaneously. It interferes with itself on the far side. It builds up at each point on the screen a probability. And then the electron arrives somewhere. One dot, one outcome. The wave function changes to reflect it. Before you look, the particle does not have a location. It has a probability of having one. The technical word for what the electron is doing in that interval is superposition. The electron between the slits is in a superposition of having gone left and having gone right. Both possibilities coexist in the wave function. Neither has been selected. This is not a shorthand for ignorance. It is the claim of the theory. The electron's position in the interval between emission and detection is not a fact. The particle did not choose a path. The particle didn't have a path. The path is what observation creates. This is Bohr's position, stated plainly. It is not a comfortable position. Einstein spent years arguing against it. His argument was that the wave function must be incomplete, a statistical description of an ensemble of particles rather than a complete description of a single one. Beneath the probabilities, he believed, lay a hidden reality with definite properties. Bell's theorem, proved in 1964, showed that any hidden reality of the kind Einstein was proposing would have to be non-local. It would have to allow instantaneous correlations across arbitrary distances. The experiments that tested Bell's theorem, performed from 1972 onward by John Clauser, Alain Aspect, Anton Zeilinger, and others, confirmed the quantum mechanical prediction every time. The 2022 Nobel Prize in Physics was awarded for this body of work. The Nobel Committee stated plainly that the experiments established something specific. The world is not locally real. Particles do not have definite properties independent of observation. Now consider the table beside you. Every atom of it contains electrons. Each electron has a wave function. Each is in constant interaction with neighboring atoms, coupling its quantum state to the states of everything around it. This process, decoherence, spreads quantum superpositions into the environment so rapidly, in timescales shorter than any instrument can resolve, that the table's quantum behavior becomes indistinguishable from classical behavior. The table looks definite. It feels solid. It is in one place. Not because its particles have definite states at the quantum level, but because their quantum behavior has been washed out by continuous entanglement with 10 to the 27th neighboring particles. Decoherence explains why quantum effects are invisible at ordinary scales. It does not explain why observation produces one specific outcome. It does not say why the electron lands where it lands rather than somewhere else. It does not close the gap between the probability distribution the wave function describes and the single dot that appears on the screen. That gap is the measurement problem. It has been open since 1925. It is still open. Here is where the implication stops being a laboratory result and becomes something else. Quantum mechanics does not contain a scale at which its rules switch off. The Schrödinger equation applies to electrons, to atoms, to molecules, to objects large enough to see under a microscope. In 2019, a team in Vienna demonstrated interference effects with molecules containing more than 2,000 atoms. The equations made the right prediction. There is no known boundary in the physics beyond which quantum behavior stops applying. Decoherence makes quantum effects unobservable at large scales. It does not eliminate them. Now go back far enough. The early universe had no macroscopic objects. Before atoms existed, before the cosmic microwave background decoupled from matter, before any structure had formed that could act as a measuring apparatus, The universe was a quantum system without an external environment to decohere it rapidly. Its state was not a classical distribution of matter arranged in definite configurations. It was a quantum superposition of configurations, enormous numbers of them, evolving according to the Schrödinger equation. The universe before the first observation may have had no definite state at all. The structure we see today emerged from that superposition. The slight density variations in the early universe that seeded the formation of galaxies were quantum fluctuations. The specific distribution of matter across the observable cosmos, the filaments, the voids, the clusters, traces back to quantum events in the first fractions of a second of cosmic history. The galaxies came from superpositions. The stars came from superpositions. The planet you're on is the amplified imprint of quantum uncertainty that preceded every possible observer by billions of years. John Bell, the physicist whose theorem proved that hidden local variables cannot explain quantum correlations, framed the central problem directly. He asked whether the wave function is a description of reality or a description of our knowledge about reality. If it is a description of reality, then reality contains superpositions, and observation collapses them into definiteness, and the question of what constitutes observation remains open. If it is a description of knowledge, then there is some deeper reality beneath quantum mechanics that we have not found, and Bell's theorem requires that deeper reality to be non-local. Neither answer is comfortable. Both have been seriously explored for decades. Wojciech Zurek at Los Alamos developed a framework called quantum Darwinism. In his picture, classical reality is what the environment has already measured and recorded in redundant copies. When a particle interacts with a detector, information about its state propagates outward through the detector's atoms, the surrounding air, the electromagnetic field, the walls. What we observe is not the quantum event itself. It is the redundant environmental record of the quantum event. We arrive second. The environment measured first. If that is correct, then every observation you have ever made is a reading of a record. The original event, the particle, the superposition, the moment of becoming definite, was something the environment processed before you arrived. You have never witnessed a quantum event directly. You have witnessed the classical echo it left in the matter around it. Take a breath. Because what comes next is the part where the word we started with gets its final meaning. We started with the word observation. We said we were going to pull it apart. Here is what is inside it. In ordinary language, observation means a mind directing attention towards something. Awareness. Consciousness receiving information about the world. When you observe a bird outside a window, something passes between the world and your mind, and afterward you know something you did not know before. That is not what quantum mechanics means by the word. In quantum mechanics, observation means the establishment of a physical correlation between a particle's state and any other physical system. The detector that fires a photon at the electron and registers the return is an observer in the quantum mechanical sense, whether or not any mind reads its display. The air molecule that collides with the electron in a moderately maintained vacuum is an observer. The electromagnetic field that the electron perturbs as it passes is an observer. Consciousness is not required. Record keeping is not required. Even a readout is not required. What is required is irreversibility, a fact. When the electron's state becomes correlated with another system in a way that cannot be undone without complete knowledge of both systems, an observation has occurred. Not because anyone looked, because a fact came into existence. The fact of which slit. The fact of which direction the scattered photon went. The fact encoded in the changed state of any system the electron touched. Observation does not mean attention. It means the creation of a fact. And now read the experimental result again with this definition in hand. Where no fact exists about which path the electron took, it takes both paths. When a fact exists, it took one. The universe's definiteness is not a baseline state that measurement disturbs. Definiteness is what measurement creates. Between measurements, between observations in this precise sense, between the moments when facts come into existence, the universe is not definite. This is what the interpretations are arguing about. Not whether the experiment is correct, it is correct. Not whether the mathematics works, it works perfectly. They're arguing about what exists in the intervals between facts. Copenhagen says nothing. Many worlds says everything. Pilot wave says something hidden. None of them have converted the others. The double-slit experiment does not sit at the edge of physics, waiting for better instruments or a breakthrough measurement that will settle the question. The result is already complete. The mystery is not empirical, it is conceptual. The physics is not missing data, it is missing a picture. A description in terms of something that is actually there. Between the observations, in the space the mathematics describes but the language cannot reach. 2 centuries of careful work have made that gap precisely visible. They have not closed it. There is a specific kind of discomfort in knowing something exactly, and being unable to say what it means. The double-slit experiment is the clearest version of that discomfort in all of science. You know the result. You can state it in one sentence. The universe behaves differently when observed, and you do not know, and no one knows, and the best theory ever built cannot say what that sentence means about the nature of what is real. The double-slit experiment happens in a room the size of a large closet. The electron travels a few inches from source to screen. The entire apparatus is unextraordinary in every physical dimension, and the principle it demonstrates operates at every scale, from the interior of your cells to the structure of the observable universe. Every chemical bond in your body is a quantum mechanical phenomenon. The covalent bonds that hold the molecules of your DNA together exist because electron wave functions from adjacent atoms overlap in ways that reduce the total energy of the system. The bond is not 2 electrons sitting at fixed points. The bond is a quantum configuration. Remove the wave nature of electrons and every molecule in your body becomes unstable. The atoms fly apart. There is no flaw beneath quantum mechanics and chemistry. It is the flaw. Quantum tunneling, the phenomenon by which particles pass through energy barriers they could not cross classically, powers every star in the observable universe. The protons in the sun's core do not have enough thermal energy to overcome their mutual electromagnetic repulsion. The temperature at the center of the sun is, by classical calculation, too low for fusion to occur at the rate it does. What allows them to fuse is the wave nature of matter. Their wave functions extend through the barrier. There is a non-zero probability of finding them on the same side. When that probability is realized, they fuse. The light reaching you right now is produced by quantum behavior that classical physics says should not be occurring. The large-scale structure of the universe, the web of filaments and voids that stretches across hundreds of millions of light years, is the amplified imprint of quantum fluctuations in the first moments after the Big Bang. The specific positions of the galaxy clusters visible in deep field images trace back to quantum superpositions that predated the first atom. The Planck satellite's map of the cosmic microwave background, the afterglow of the early universe, shows temperature variations of 1 part in 100,000 across the sky. Those variations match the predictions of inflationary quantum cosmology to better than 1%. The large-scale structure of the cosmos is a classical record of quantum interference from before the first star. The classical world you walk through is built from particles whose paths do not exist until something makes them exist. The table is solid. The The floor holds your weight, the room looks definite and stable, and every particle of it is a quantum system whose properties before interaction are described by wave functions, not by positions and velocities. The classical appearance is produced by decoherence, by the continuous entanglement of every particle with every neighbouring particle, washing quantum coherence into the environment faster than any observable effect can accumulate. The appearance is real, it is reliable, you can build civilization on it, but it is an appearance. What produces it, at the level where the production actually occurs, is the thing the double slit experiment shows. You're not watching the quantum world from a safe classical vantage point, you're made of it. The wave nature of matter is not a feature of small systems. It is the mechanism by which everything that exists came to be and continues to hold together. If you needed that slowly, the rest of tonight is yours. This was worth taking seriously. We started with a word, observation, the most ordinary word in the vocabulary of science. Every experiment ever performed is described in terms of it. Every result is an observation. Every measurement is an observation. The word appears so naturally in so many contexts that it seems transparent, like a window you look through without noticing the glass. The double slit experiment is what happens when you try to look at the glass. The electron goes through both slits when no observation occurs. It goes through one when it does. The word sits at the centre of that change, apparently explaining it. You observe, the pattern changes. Simple. Except that when you try to say what observation actually requires, the word opens into something you did not expect. Not attention, not consciousness, the creation of a fact, a physical correlation between the particle's state and any other system in the universe, an irreversible record, a moment when something that was indefinite becomes definite, not because anyone was watching, but because the conditions for watching were present. The ball from the beginning of tonight goes through one hole or the other. It does this because its interaction with the air, the surface of the wall, the electromagnetic fields of the atoms it passes near constitutes an uninterrupted observation in the quantum mechanical sense. The ball is being continuously measured by its environment, every particle of it, every moment of its trajectory. Classical behaviour is not the absence of observation. It is observation so continuous and so dense that quantum superpositions cannot survive long enough to accumulate into visible effects. The electron in the double slit experiment is not a strange object. It is what every particle is, under conditions of sufficient isolation. The ball's classical behaviour is not what particles really do. It is what particles do when they are constantly observed by everything around them. The universe is not divided into a quantum realm and a classical realm. It is one realm. The classical appearance is the surface. The quantum behaviour is what is actually there. An observation, in the precise sense the experiment demands, is not something humans do to nature. It is something nature does to itself, continuously, through the entanglement of every particle with every other. What we call measurement is simply a moment when that ongoing process becomes legible to us. When the record the environment has already made is transferred to a form we can read. What was the electron doing before it became legible? The mathematics says it had a wave function. The wave function says it was everywhere it could have been, with probabilities. The interpretations disagree about whether that description is complete or partial, whether one universe branched or all possibilities remained, whether a pilot wave was guiding it along a hidden path. None of them agree. None of them have convinced each other. The gap between the calculation and the picture is the same width it was in 1925. Thank you for staying with this all the way through. If tonight gave you something worth carrying, a subscribe helps this channel reach more people who want exactly this kind of careful, unhurried evening. You cannot unknow this. The crisis in physics that the double-slit experiment sits at the centre of did not arrive suddenly. It built over 3 decades, one uncomfortable result at a time, each one suggesting that something was wrong with the clean categories of particles and waves. By the time physicists first fired single electrons at 2 slit barriers in the 1920s, they already knew that the classical framework was in trouble. What the double-slit experiment did was show precisely where the trouble lived. In 1923, Arthur Compton at Washington University in St. Louis scattered X-rays off electrons and found that the scattered X-rays had longer wavelengths than the incoming beam. The change in wavelength depended on the angle of scattering in exactly the way you would calculate if the X-ray were a particle, a photon, colliding with the electron like one billiard ball hitting another. A wave does not behave this way. When a wave scatters, its wavelength does not change based on the angle of scatter. Compton's result was particle behaviour, unmistakably. The Nobel Committee awarded him the prize in 1927. Light, which Young had shown in 1801 was definitively a wave, was also definitively a particle. Louis de Broglie, a French doctoral student, asked the obvious question in his 1924 thesis. If light, assumed to be a wave, turned out to also behave as a particle, why should matter, assumed to be particles, not also behave as waves? He wrote down a simple equation relating the momentum of any particle to a wavelength. The wavelength was inversely proportional to the momentum. For a baseball, the calculated wavelength was so small that no physical consequence could result. For an electron, it came out to a scale comparable to the spacing between atoms in a crystal. De Broglie's thesis examiner sent it to Einstein before approving it. Einstein said the student had lifted a corner of the Great Veil. The committee passed him. 3 years later, Clinton Davison and Lester Germer at Bell Labs in New York were studying how electrons scattered off a nickel crystal surface when their vacuum chamber cracked, oxidized the crystal, and forced them to heat the sample to clean it. Heating converted the polycrystalline surface to a single crystal. When they resumed the experiment, the electron scattering pattern had changed. The electrons were diffracting off the crystal lattice planes in exact agreement with de Broglie's wavelength formula. At the same time, George Paget Thomson in Scotland obtained electron diffraction rings by passing electrons through thin metal foils. Both groups confirmed the same thing. Electrons were waves. Both groups won Nobel Prizes. De Broglie won his in 1929. So by 1927, when Werner Heisenberg assembled his matrix mechanics, and Erwin Schrödinger wrote down his wave equation, the situation was this. Light was both a wave and a particle. Electrons were both a wave and a particle. The categories that organized the world for 3 centuries were insufficient to describe what anything actually was. The new theory, quantum mechanics, was built to contain this contradiction without resolving it. It described particles using wave functions. The wave function evolved as a wave. The particle arrived as a particle. What the thing was in between during its travel, the theory declined to say. This was not a temporary omission. It was a structural feature. The founding generation of quantum mechanics, Bohr, Heisenberg, Born, Dirac, Pauli, understood that the theory was not a picture of reality. It was a procedure for calculating outcomes. And the procedure worked with an accuracy that has never been matched. Every attempt to complete the picture, to say what the particle was between measurements, has run into either the measurement problem or Bell's theorem or both. The incompleteness the founders acknowledged in 1927 is still present in the theory today. The double-slit experiment did not create this situation. It made it visible in a single, inarguable experimental result that no amount of theoretical adjustment has resolved. Let that rest for a moment before we take it further. Before a detector enters the picture, the interference pattern exists. 1 electron at a time, months of accumulation. The pattern is not ambiguous. It is not a rough approximation. It matches the mathematical prediction for two-slit interference from a particle of the electron's mass and energy with a precision that leaves no room for alternative explanation. The mathematics behind the pattern is specific. The positions of the bright bands are determined by the condition that the path lengths from the two slits to any given point on the screen differ by an integer multiple of the electron's de Broglie wavelength. The positions of the dark bands are where path lengths differ by a half-integer multiple. The widths of the bands, the angles between them, the way they shift when the slit spacing changes, all of it is predicted exactly by the two-slit interference formula derived from wave mechanics. There is no parameter to adjust. The prediction is what the prediction is. The experiment confirms it every time. This mathematical precision is what makes the results so difficult to dismiss. The interference pattern is not a vague tendency for electrons to avoid certain regions of the screen. It is a specific, quantitatively confirmed pattern that requires exactly two coherent sources, one at each slit, contributing simultaneously to each electron's arrival location. The electron went through both slits. Not probably. Not figuratively. The pattern cannot be produced by any other mechanism. Richard Feynman, who spent more time thinking about the foundations of quantum mechanics than almost anyone in the 20th century, came to a precise view of what this meant. In his formulation of quantum mechanics, called the path integral or sum over histories approach, the probability of a particle travelling from one point to another is calculated by summing the contributions of all possible paths the particle could take between those points. Not the most probable path. All paths. Every path, no matter how indirect or geometrically strange, contributes an amplitude. Most amplitudes cancel against each other because nearby paths have similar phases that average out. The paths near the classical trajectory tend to reinforce, which is why classical mechanics is recovered at large scales. But in the double slit experiment, paths through the left slit and paths through the right slit contribute amplitudes that interfere at specific points on the screen. The pattern of reinforcement and cancellation is the interference pattern. In Feynman's formulation, asking which slit the electron went through is asking which contribution to the sum you want to count. The answer is both. The mathematics requires both. The pattern is both contributions added together, and when a detector at one slit removes the contribution of the other, the pattern that remains is not the interference pattern, it is what you get from one slit only. Feynman described this result, in his lectures on physics and in his popular writing, as the central mystery. He said everything else in quantum mechanics, every other strange result, every other philosophical puzzle, was contained inside this one experimental setup. He was not speaking loosely. The double-slit experiment is the complete exhibition of what quantum mechanics says about the relationship between particles and the paths they take. Which hole did the electron use? Both. And when you try to find out which one, it uses one. Those are not contradictions, they are the data. The interpretations disagree about what is happening behind the data. But there is one question the data itself has settled, and settled recently enough that it is still being absorbed. For decades after the 1920s, the most natural escape from the double slits implications was hidden variables. Perhaps quantum mechanics was correct as a practical tool but incomplete as a description of reality. Perhaps behind the probability distribution described by the wave function, particles had definite properties the theory simply failed to know. Definite positions, definite paths. A hidden layer of reality that determined all outcomes while remaining inaccessible to any current measurement. The apparent randomness would be an artifact of ignorance, the same way a coin flip seems random until you know the precise angle and force of the throw. Einstein held this view. He never accepted that the electron had no definite location before measurement. He believed the incompleteness was in the theory, not in nature. God, he said, does not play dice. In 1964, John Bell at CERN proved a theorem. Bell showed that any theory in which particles carry hidden local properties, properties that are definite regardless of whether anyone measures them and that do not propagate their influence faster than light, make specific, testable predictions about the correlations between measurements on pairs of particles that have interacted. He derived an inequality that any such hidden local variable theory must satisfy. Then he showed that quantum mechanics predicts violations of this inequality. If Einstein was right, Bell's inequality would hold. If quantum mechanics was right, it would be violated. The experiments began in 1972. John Clauser and Stuart Friedman at Berkeley performed the first serious test. Their results favoured quantum mechanics. In 1981 and 1982, Alain Aspect and his colleagues in Paris ran a more definitive series, using pairs of entangled photons and switching the measurement settings after the photons had already departed the source, closing the loophole that said the photons might have carried correlated instructions from their origin. Aspect's results violated Bell's inequality by many standard deviations. Anton Zeilinger and colleagues in Vienna performed increasingly refined versions through the 1990s and 2000s, closing further loopholes. In 2022, the Nobel Prize in Physics was awarded to Clauser, Aspect and Zeilinger. The Nobel Committee stated that their work established that the world is not locally real. Not that some quantum systems have unusual properties. That reality itself, as a general feature of the universe, lacks local realism. Particles do not have definite properties before measurement that are independent of the act of measuring. This is not an interpretation. It is not a preferred philosophical position. It is the conclusion of experimental tests performed over 5 decades and confirmed with enough certainty to justify the highest scientific honour. The hidden variable escape route that Einstein preferred is closed. The electron did not secretly have a path. The definiteness that measurement produces is not a revelation of a pre-existing fact. It is the creation of a fact. The 2022 Nobel Prize is the most recent chapter in a story that began with Thomas Young in 1801. The story says the same thing it has always said. The universe behaves differently when observed. And now we know that this cannot be explained by hidden facts we happen not to know. The observation is not uncovering the real. The observation is making the real. Hold that for a moment. It is worth letting it land before we take the next step. In 1935, Erwin Schrödinger, one of the architects of the equation that carries his name, wrote a paper intended to illustrate what he considered an absurdity in the Copenhagen interpretation. He succeeded in illustrating the absurdity. He also succeeded in illustrating something he did not intend, which is that the absurdity might not be escapable. The thought experiment is familiar. A cat, a sealed box. Inside the box, a radioactive atom with a 50% chance of decaying in 1 hour. A Geiger counter, a vial of poison, a mechanism that shatters the vial if the counter clicks. After 1 hour, according to quantum mechanics, the atom is in a superposition of decayed and undecayed. Since the atom drives the mechanism, and the mechanism drives the vial, and the vial's state determines the cat's, the entire system, atom plus mechanism plus vial plus cat, is in a superposition. The wave function assigns equal probability to a dead cat and a live one. Schrödinger's intention was to show that this result was absurd. Cats are clearly either alive or dead. They're not in superpositions of both. Therefore, he argued, applying quantum mechanics to macroscopic systems in this way must be wrong. The theory needed a boundary, a specification of where superposition stops being the correct description and classical definiteness takes over. 90 years later, the boundary remains unspecified. Decoherence explains why the cat's superposition In any realistic closed box with a real cat and real air and real walls, decoheres in timescales so short that its quantum behavior is for all practical purposes classical. The cat interacts with far too many particles too quickly to maintain any detectable superposition. But decoherence does not eliminate the superposition, it spreads it into the environment. In the many worlds picture, the cat is genuinely in a superposition, and the universe branches when the box is opened. In the Copenhagen picture, the cat was in a superposition, and the wave function collapsed when a measurement occurred, but what counted as the measurement remains undefined. In the pilot wave picture, the cat was always in one state, guided by the pilot wave, but the pilot wave's configuration was not knowable without tracking every particle in the box. The cat thought, experiment survives because it points at the same gap the double slit experiment points at, in a form that is impossible to make abstract. You are forced to ask, is the cat alive or dead before you open the box? Your intuition says yes. The theory does not say yes. The theory says the cat is in a superposition until an observation occurs, and what counts as an observation is not specified by the theory. Schrödinger wanted to refute the theory by making it seem absurd. What the experiment actually showed is that either the theory is wrong in some way not yet detected, or the situation with the cat is genuinely as strange as the situation with the electron. The cat is larger, warmer, and far more thoroughly entangled with its environment than the electron, but it is made of the same things, and the same rules apply. The universe does not offer a separate set of rules for objects you can hold. There is a precise name for the gap that all of this has been circling, the measurement problem. It has been open since Born proposed the probabilistic interpretation of the wave function in 1926. It remains open today. No interpretation of quantum mechanics has solved it in a way that has persuaded the physics community. The disagreement is not about the data, it is about what the theory means. Here is the measurement problem stated as clearly as possible. The Schrödinger equation describes how wave functions evolve. It is linear, deterministic, and precise. Given the wave function of a system at one moment, the equation tells you exactly what it will be at every future moment. The equation never produces a definite single outcome. If the electron is in a superposition of going left and going right before the measurement, and the measuring apparatus is included in the system, the Schrödinger equation evolves the combined system into a superposition of apparatus registered left and electron went left and apparatus registered right, and electron went right. Both outcomes continue to exist in the combined wave function. The equation does not select one, but measurements produce single outcomes. You see one dot on the screen. The detector registers one click. The physicist records one result. The single outcome is the universal experience of everyone who has ever performed or read about a quantum mechanical measurement. The theory does not explain the transition from the superposition the equation describes to the single outcome that experience confirms. This is the measurement problem, not why quantum mechanics is strange, why quantum mechanics, applied rigorously to its own measuring apparatus, fails to produce the definiteness that every measurement actually shows. Copenhagen's answer is, the wave function collapses at the moment of measurement, but the collapse is not in the Schrödinger equation. It is an additional postulate added to the theory, not derived from it. What triggers the collapse is undefined. How fast it occurs is undefined. Whether it requires a macroscopic system, or a conscious observer, or simply any irreversible interaction, is undefined. Many worlds' answer is, the wave function never collapses. Both outcomes occur. The physicist who registers left is in one branch. A version of the physicist who registers right is in another. Both are real. The single outcome each physicist experiences is real because each branch is a separate, non-interfering part of the universal wave function. The definiteness is not a physical transition from superposition to one outcome. It is the subjective experience of a particular branch. Pilot wave's answer is, there is always a definite outcome because the particle always has a definite position, guided by the pilot wave. The superposition is a property of the wave, not the particle. The measurement reveals where the particle was all along. The definiteness is always there. You just could not predict it from the wave function alone. These three answers have been debated since the 1920s, the 1950s and the 1950s respectively. None has converged to acceptance. None has been falsified. They are not distinguishable by any experiment yet performed, because they all make the same predictions for every experiment. They are distinguishable only by what they require you to believe about reality in the intervals between experiments. And on that question, reasonable physicists have disagreed for a century without resolution. The measurement problem is not a gap in the data. It is a gap in the picture. The theory works perfectly. What it is a picture of is contested. You do not need to resolve this tonight. No one has. Let that sit with you in whatever form it arrived. The quantum eraser experiment deserves its own section, because it is the result that most precisely identifies what kind of strangeness we are dealing with. The mechanical disturbance explanation. The idea that the detector physically bumps the electron, and this is why the pattern disappears, predicts that erasing the record afterward should make no difference. The bump has already happened. The electron has already been deflected. Whatever damage the measurement did is done. The quantum eraser shows that this prediction is wrong. The experiment, first proposed by Marlon Scully and Kai Druhl in 1982 and performed in various forms through the 1990s and 2000s, works like this. The electron passes through the two slits. At one slit, a device marks the electron in a way that records which path it took, but without transferring significant momentum. The marking is done through quantum entanglement. The electron's which path state becomes correlated with the state of a separate particle, the marker, without a physical collision. The electron then travels to the screen. Because a which path record exists in the marker, no interference pattern forms. Now, before the results at the screen are analysed, the markers are sorted. Half the markers are sent to a detector that reads which path. Half are sent to a device that erases the which path information entirely, scrambling the correlation so that the path cannot be recovered even in principle. When the screen results are separated into two groups, those corresponding to markers that were read and those corresponding to markers that were erased, the results are different. The red group shows two stripes. No interference. The erased group shows the interference pattern. The physical interaction with the electron was the same in both cases. The same entanglement occurred. The same marking happened. The only difference is whether the which path information survived or was destroyed, and the electron's behavior at the screen reflects that difference. The electron did not go back in time. The electron did not receive a signal from the eraser. The electron arrived at the screen before the erasure decision was made, and yet the distribution of where electrons landed, analysed after the fact by sorting them into the erased group and the read group, shows that the electrons whose markers were erased produced an interference pattern, and the electrons whose markers were read did not. This result is confirmed. It has been repeated by multiple groups. It is consistent with quantum mechanical predictions, and it does not fit any classical story in which the electron travels from source to screen through one definite path and arrives at a definite location for physical reasons that are independent of what happens to a separate particle afterward. The pattern is sensitive to information, not to force, not to physical contact, to whether a fact about the electron's path exists in any physical system, anywhere in the universe, at the time the pattern is analysed. That is the result. It is not a philosophical position. It is a measurement. Take a breath here. because the next step is the part where we look at what this implies about the universe before any measuring apparatus existed at all. John Archibald Wheeler, who spent his career at Princeton and the University of Texas and who worked with both Bohr and Einstein at different points, had a specific question. If the interference pattern is produced by the electron going through both slits, and the two-stripe pattern is produced by the electron going through one, and the choice between these outcomes depends on whether which path information is obtained, then when exactly does the choice get made? Is it made when the electron passes through the slits, or can it be made afterward? Wheeler designed an experiment to test this. In his version, the electron is allowed to pass through the two slits without a detector in place. At this point, if the electron behaves normally, it should be in a superposition of both paths, on its way to producing an interference pattern. Then, after the electron has already passed through the slits, but before it has reached the screen, the experimenter decides whether to insert a detector. If the decision to measure which path is made after the electron has cleared the slits, and if the electron was already committed to a both paths superposition, inserting the detector at that late stage should make no difference. The interference pattern should form regardless. The experiment shows that inserting the detector after the electron has cleared the slits still destroys the interference pattern. The decision to measure, made after the electron passed through the slits, changes what the electron is recorded to have done at the slits. This has been performed experimentally. In 1984, Carol Alley and colleagues at the University of Maryland performed a version with photons. In 2007, a French team led by Vincent Jacques confirmed it with single photons in a refined version that closed several loopholes. In 2012, Andrew Truscott at the Australian National University performed a version with single helium atoms that ruled out further alternatives. The results agree with quantum mechanical prediction every time. Wheeler interpreted this as evidence that the past is not fixed until the measurement that establishes it is made. The electron did not go through one slit or both slits at the moment of passing through the barrier. That question did not have an answer until the choice of measurement was made, possibly later. He called this the participatory universe. The act of observation, even retroactively applied, participates in establishing what happened. This is not a comfortable position. It is Wheeler's position, arrived at after decades of considering what the experimental results actually require. He was not a philosopher speculating. He was one of the physicists who helped build the understanding of quantum mechanics in the 20th century, and his conclusion was that the past is not simply there, waiting to be discovered. It is established by the choices made about how to examine it. If you find this deeply uncomfortable, that discomfort is the correct response. The experiment is not ambiguous, the result is what it is. And it implies something about the relationship between observation and reality that has no analogue in any other area of science. We have now assembled all the pieces. The electron goes through both slits when unobserved. It goes through one when observed. The observation is not a physical act in the ordinary sense, but the creation of a fact. The fact can be created anywhere, by any physical system, and can in principle be erased. If erased, the pattern returns. The decision to create or erase the fact can be made after the electron has already passed through the slits. The 2022 Nobel Prize confirmed that hidden local variables cannot explain any of this. What is the electron between observations? What is anything between observations? The question has three answers currently on offer, corresponding to the three major interpretations. In the Copenhagen picture, the question has no answer, not because the answer is hidden, because the question is malformed. Asking what the electron is doing between observations is asking about something the theory does not and cannot describe. The wave function is not a description of the electron between measurements. It is a tool for calculating the probabilities of measurement outcomes. What the electron is in the interval between measurements is not a question physics can answer, on the Copenhagen view, because physics is a description of measurement outcomes and nothing else. In the many-world picture, the answer is the electron is in all the states the wave function allows, simultaneously, in different branches of the universal wave function. Between observations, the wave function evolves smoothly according to the Schrödinger equation. The branching that occurs at measurement does not involve a collapse. It involves the entanglement of the measuring apparatus with the measured system, creating a superposition of both outcomes, which then decohere into separate branches. Between observations, the electron is genuinely everywhere the wave function says it might be, across all branches. In the pilot wave picture, the answer is the electron is in one specific location, guided along a definite path by the pilot wave. Between observations, the electron travels a real trajectory. The pilot wave goes through both slits and interferes. The particle follows the wave, ending up where the wave's guidance takes it. Between observations, the electron is somewhere. You cannot know where without knowing the initial conditions precisely, but it is somewhere. 3 pictures, 3 answers to the same question. No experimental result can distinguish between them because they all predict identical outcomes for every experiment. The choice between them is a choice about what you are willing to believe about what is not measured, and that choice has been made differently by thoughtful physicists for a century. The electron between observations is either nowhere in particular or everywhere simultaneously across branching realities, or somewhere specific but unknown. These are the options. None can be confirmed, none can be ruled out. And from this uncertainty, the most precisely confirmed theory in the history of science continues to produce predictions that match experiments to 1 part in a trillion. The theory works perfectly. The picture is missing. That combination, working theory, absent picture, is the condition physics has been in since 1925. It is not a temporary situation waiting for a better experiment. It is the current state of the foundations of the field. The universe does not seem to require a picture. The universe seems content with the predictions. What requires the picture is us. The double-slit experiment is performed in a carefully isolated chamber. The electron travels through a near-perfect vacuum. Nothing touches it between source and screen. The result requires this isolation. 1 stray air molecule is enough to act as a witch-path detector and collapse the interference pattern. The quantum behavior is visible precisely because it has been protected from the environment. Outside the chamber, in every object in the room, the quantum behavior is present but invisible, hidden by the continuous, rapid, unavoidable entanglement of every particle with every neighboring particle. The environment performs an unending series of witch-path measurements on every particle it touches, and the particles respond accordingly, behaving classically because they are being constantly observed by everything around them. But the quantum behavior does not disappear. It simply operates below the threshold of classical observation, and its effects accumulate into the macroscopic world in ways that make the macroscopic world possible. Every chemical bond in your body is a quantum mechanical phenomenon. The covalent bond that holds 2 hydrogen atoms together in a water molecule exists because the electron wave functions of the 2 hydrogen atoms overlap in the space between the nuclei. The electrons are not sitting at fixed positions between 2 protons. They are in a quantum configuration in which the probability of finding an electron is higher in the bonding region than elsewhere. This configuration reduces the total energy of the combined system compared to 2 separate atoms. The bond is the energy minimum. The stability of the bond is a consequence of the wave nature of electrons and the way wave functions overlap and interfere. Remove the wave nature of electrons and covalent bonds disappear. Without covalent bonds, molecules do not form. Without molecules, chemistry does not exist. Without chemistry, biology does not exist. Without biology, you do not exist. The fact that you are sitting somewhere reading this is a consequence of the same physics that produces the interference pattern in the double-slit experiment. The enzyme that processes glucose in your cells has an active site whose geometry is maintained by the quantum configuration of its electrons. The DNA in every cell of your body stores information through hydrogen bonds, whose selectivity depends on quantum mechanical overlap between specific molecular orbitals. The nerve signals that make consciousness possible travel along ion channels, whose selectivity for specific ions, which ions can pass through and which cannot, depends on quantum mechanical interactions between the ions and the protein structure of the channel. You are not a classical object that quantum mechanics affects at the margins. You are a quantum mechanical system whose large-scale behavior appears classical because of decoherence. The machinery that maintains you is quantum mechanical all the way down. Nuclear fusion, which powers every star in the observable universe, requires quantum tunneling. The protons in the sun's core carry positive electric charge. Like charges repel. Two protons approaching each other at the temperatures achievable in stellar interiors do not have enough kinetic energy to overcome the electromagnetic repulsion classically. The temperature at the centre of the Sun is, by classical calculation, too low for fusion to occur at the rate needed to maintain the Sun's luminosity. What allows protons to fuse is the wave nature of matter. A proton's wave function extends into the region of the nuclear force, even when the proton's kinetic energy is insufficient to reach there classically. The probability is small but non-zero. When it is realized, the two protons fuse and release energy. The light that reaches Earth, that has reached Earth for 4.5 billion years, is the accumulated product of quantum tunneling events in the Sun's core. Quantum mechanics is not a curiosity of laboratory physics. It is the engine of stellar energy. The large-scale structure of the universe is the amplified imprint of quantum fluctuations in the first moments after the Big Bang. In the very early universe, before atoms existed, before any macroscopic structure had formed, the universe was a quantum system in a superposition of density configurations. Quantum fluctuations created regions of slightly higher and slightly lower density, spread across the young universe in a specific statistical pattern, determined by the quantum mechanical properties of the inflaton field. Over the following 13 billion years, gravity amplified these slight variations. Denser regions attracted more matter. They grew into galaxies, then galaxy clusters, then the cosmic web of filaments and voids that structures the observable universe at the larger scales. The Planck satellite, which mapped the cosmic microwave background in precise detail between 2009 and 2013, produced a map of the temperature variations in the afterglow of the early universe. Those temperature variations trace the original density fluctuations. Their statistical properties match the predictions of inflationary quantum cosmology to better than 1%. The specific distribution of galaxies across the observable universe, the fact that galaxies are here and not there, is determined by quantum mechanical events that occurred in the first fraction of a second of cosmic history. The interference pattern in the double-slit experiment is a visible version of the same physics that determines the large-scale structure of the cosmos. The two-slit interference pattern and the distribution of galaxies across the sky are both produced by the same principle. Quantum superpositions evolving and producing definite outcomes when observation, in the technical sense, occurs. The universe is quantum mechanical from its foundations to its largest structures. The classical appearance is real and reliable at the scales where you live, and it is an appearance. There is a lot to absorb there. Take a breath. We're almost at the end, and the word we started with, observation. has been through something over the course of tonight. We started with the ordinary meaning, attention, a mind directed toward the world, a person looking through an eyepiece, or reading a data output, or watching a screen. That meaning is so natural, so embedded in how we talk about science, that it seems self-evident. Observation is what scientists do. They look at things. The things get observed. Data results. Then the double-slit experiment showed that something changes when the electron is observed. The interference pattern vanishes. The electron stops going through both slits and starts going through one. The words seem to name the mechanism. Observation was causing the change. But what the experiments actually show is that the change is caused by information, not attention. The detector running in an empty room produces the same result as the detector read by a physicist. The which path information stored in a quantum marker that is never read produces the same result as information that is read. The deciding factor is not whether anyone is watching. It is whether a fact about the electron's path exists anywhere in the physical world. So observation, in the quantum mechanical sense, means the establishment of a physical correlation between a particle's state and any other system, in a way that creates a fact about the particle's property. Consciousness is not required. Record-keeping is not required. A readout is not required. What is required is irreversibility. The moment when the electron's which path state becomes encoded in the state of another physical system in a way that cannot be undone without complete knowledge of both, an observation has occurred. This meaning of observation has been sitting in the mathematics of quantum mechanics since Born proposed the probabilistic interpretation in 1926. It took decades of increasingly precise experiments to isolate it. The quantum eraser showed that physical interaction without persistent information does not destroy the pattern. The Wheeler delayed choice showed that the timing of the information creation before or after the electron cleared the slits made no difference. The Bell inequality experiments showed that hidden local facts about the electron, waiting to be discovered, cannot explain the results. What remained was the conclusion. Observation is the creation of a fact, and facts are what make the universe definite. Between facts, between observations, between the moments when correlations are established and irreversibility sets in, the universe is not definite. It is not secretly definite and merely unknown to us. The Bell experiments ruled that out. It is genuinely, as a matter of experimental fact, not locally real in the interval before observation. What it is exactly, in that interval, is what the interpretations argue about, and what they have been arguing about for a century. The word observation, which you used without a second thought this morning when you glanced out a window, has a meaning in physics that contains within it the entire unsolved problem of the foundations of quantum mechanics. A century of experiment has made the problem more precise. It has not made the answer more available. Some questions do not resolve, they clarify. The double-slit experiment has been clarifying the same question since Young first observed the interference pattern in 1801. The question is not harder to state than it was. It is now stated with extraordinary precision. The universe is different when observed. Observation means the creation of a fact. Between facts, the universe is indefinite. What indefinite means exactly, at the level where something is real but not definite, is the question that remains. Every attempt to recover a classical picture of the electron in the double-slit experiment runs into a specific, independent failure. The failures do not share a common cause. Each one addresses a different route to the same destination, and each one closes that route separately. Together they constitute a compounding barrier that has not been penetrated in a century of work. The first barrier is physical disturbance. the detector physically interacts with the electron and scrambles its trajectory. This is the most natural explanation, and it contains something real. Heisenberg's uncertainty principle ensures that measuring position with sufficient precision does disturb momentum. But the quantum eraser experiments show that this is not the mechanism responsible for destroying the interference pattern. Erasing the witch path record restores the pattern even though the physical interaction has already occurred. Physical disturbance is a real effect that is not the cause. The second barrier is hidden variables. Perhaps the electron carries definite properties at all times, properties that quantum mechanics fails to describe. The apparent randomness is ignorance, not nature. The electron went through one slit all along. We simply did not know which one. Bell's theorem, confirmed experimentally from 1972 to 2022, proves that local hidden variables cannot reproduce the correlations quantum mechanics predicts. The electron did not carry the information about which slit it would use. The information was not there to carry. The third barrier is decoherence. Perhaps the environment acts as a continuous observer, and sufficiently isolated systems never really show quantum behavior outside the laboratory. But experiments with molecules of 2,000 atoms demonstrate quantum interference in conditions of sufficient isolation. The principle does not stop at any known scale. Decoherence explains why quantum effects become unobservable in ordinary conditions. It does not eliminate them. And in the early universe, before any environment capable of rapid decoherence existed, the quantum behavior was operating at cosmic scales. The fourth barrier is the measurement problem itself. Perhaps a more complete theory will be developed, one that describes what happens at the moment of measurement without the ad hoc collapse postulate Copenhagen requires. Perhaps that theory will restore a classical picture of particles with definite properties between measurements. But every proposed completion of quantum mechanics either requires non-locality, as pilot wave theory does, or requires a vast proliferation of realities, as many worlds does, or requires making measurement the undefined primitive from which everything else follows, as Copenhagen does. None of these is a classical picture. None of them avoids the strangeness. They relocate it. These four barriers are independent. Removing any one of them does not affect the others, and they form a stack. The physical disturbance explanation is ruled out by the quantum eraser. The hidden variable explanation is ruled out by Bell. The decoherence boundary explanation is ruled out by large molecule interference. The completion of theory explanation is constrained by the requirement of non-locality or proliferation of worlds. 4 independent barriers, each one fatal to the classical picture independently. Together they form a compounding structure that has resisted a century of attack by the most technically sophisticated scientific community in history. The electron is not classical. The universe is not locally real. Between observations, in whatever sense that phrase can be given, reality does not have the properties classical physics assumes it must. These are not theoretical preferences. They are the content of confirmed experimental results. Sit with that for a moment, not as a cause for alarm, as a cause for precision. The universe is stranger than the categories you were given. That is not a failure of the categories. It is an accurate description of what the experiments have found. Now consider what this means for the word we have been pulling apart all evening. Observation, in the technical sense the double-slit experiment requires, is the creation of a fact in the physical world, and the fact does not need to be observed by any mind. It does not need to be read by any person. It does not need to be preserved in any record that anyone will ever access. What it needs to be is irreversible. A physical correlation between the particle and another system, established in a way that cannot be undone without complete knowledge of both. The universe monitors itself. Every particle that interacts with another particle performs, in this technical sense, an observation. The air in this room is performing observations on every surface it touches, continuously, at the rate of approximately 10 to the 28th collisions per second. The electromagnetic field permeating the room is performing observations on every charged particle within it. The gravitational field is coupling the quantum states of every massive object to every other. The environment is an unceasing, distributed, universal measuring apparatus, making facts out of superpositions at a rate that makes human observation vanishingly slow and rare by comparison. What you call observation, when you look at something, is a moment when the process the environment has already been performing continuously is transferred to a form that your nervous system can process. You arrive at the end of a chain of witch path measurements that the world has already made. You read the record. You are not the first observer. The room was, and before the room, before planets, before stars, before the first atom. What was the universe then? What observations had been made? What facts existed? The mathematics says the universe existed in a quantum superposition of configurations. The wave function of the universe was evolving according to the Schrödinger equation. Definite facts were sparse. Most of what existed was potential, spread across the wave function, not yet collapsed into any specific configuration by observation in any form. From that superposition, through a process whose details are still argued about, the universe we inhabit emerged. Quantum fluctuations became density variations. Density variations became galaxies. Galaxies became stars. Stars became planets. Planets became chemistry. Chemistry became biology. Biology became observation in the human sense. And observation in the human sense is now asking what observation in the quantum mechanical sense actually means. We are the universe asking itself what it is between the moments when it is watching itself. That is not a poetic gloss. It is a description of what the experiment shows. The de Broglie wavelength of an electron moving at a few percent of the speed of light is approximately 1/10 of a nanometer. 1/10 of a nanometer is the typical distance between atoms in a crystal lattice. It is also, not coincidentally, the scale at which electron interference effects were first observed when Davison and Germer scattered electrons off a nickel crystal in 1927. The wavelength that de Broglie calculated from his 1924 formula, years before the experiment that confirmed it, matched the crystal spacing to the precision available in the measurement. This is what a correct prediction looks like in physics. Not approximately right. Exactly right, within measurement error derived from an equation written before the evidence existed. The experimental confirmation cascade that followed de Broglie is worth tracing precisely, because it shows how the classical world was dismantled piece by piece, by results that each, individually, seemed manageable, but that together constituted a complete revision of what matter was. 1897. Thomson identifies the electron as a particle with definite charge and mass. 1905. Einstein proposes the photon, giving light particle properties. 1913. Bohr models the atom using quantized electron orbits, the first direct application of quantum conditions to atomic structure. 1923. Compton confirms photons have momentum and transfer it like particles in collisions. 1924. De Broglie proposes matter waves. 1925. Heisenberg develops matrix mechanics. 1926. Schrödinger develops wave mechanics. Born proposes the probability interpretation of the wave function. 1927. Davison and Germer confirm electron diffraction. Heisenberg derives the uncertainty principle. The Copenhagen interpretation is articulated. The double-slit experiment with individual electrons becomes conceptually central to the field, demonstrating in its simplest form the full content of what the new theory was saying. Each of these results landed in a physics community still hoping the classical picture could be preserved with minor modifications, Each one made it harder. By 1927, the classical picture was gone. What replaced it was not a picture at all. It was a procedure, a precise, powerful, experimentally confirmed procedure for calculating measurement outcomes, with no agreed account of what reality was between measurements. That is where the field has been ever since. The young physicists who built quantum mechanics in the 1920s had names that became famous: Heisenberg, Schrödinger, Dirac, Pauli, Born. They were in their 20s. They were working faster than any previous generation in physics had worked, driven by the pressure of experimental results that demanded a new framework and the awareness that they were building something historically unusual. Heisenberg, in the summer of 1925, derived his matrix mechanics while recovering from hay fever on a windswept North Sea island, working through the night and watching the sun rise over the water, having completed the first consistent formulation of quantum mechanics. Schrödinger derived his wave equation in December 1925 during a vacation, under circumstances his biographers have been diplomatically vague about. Dirac synthesized the two approaches in early 1926, showing they were mathematically equivalent. The theory was assembled in less than 2 years from scratch by people who were simultaneously dismantling the century-old framework they had been trained in. None of them agreed on what it meant. Heisenberg and Bohr held to Copenhagen. Schrödinger found the probabilistic interpretation he had contributed to philosophically unacceptable and spent years trying to argue against it using his own equation. Einstein never accepted it. De Broglie initially proposed a pilot wave version and then abandoned it under pressure from the Copenhagen Consensus before Bohm revived and developed it in 1952. The founders could not agree. The disagreement was transmitted to the next generation. It has continued to the present. The experiment that sits at the center of all of this, the double-slit experiment with single electrons, has been performed with increasing precision for nearly a century. The result has never changed. The interference pattern forms when which path information is absent. It vanishes when which path information is present. The pattern responds to information. Reality responds to observation. The precise meaning of observation remains contested. In laboratories today, as you are here, the experiment is still running in various forms. Single electrons, single photons, single atoms, molecules large enough to have an internal structure, all going through barriers with 2 openings, all producing interference patterns that require them to have traversed both openings simultaneously, all revealing the pattern only when no which path record exists anywhere in the universe. The result does not age. It does not become less strange with repetition. The 1000th confirmation carries the same implication as the first. You cannot explain it away. 4 independent barriers close every classical route to an explanation. You cannot explain it by ignoring it, because the GPS system in every phone on the planet depends on quantum mechanical predictions that follow directly from the same framework. You cannot explain it by waiting for a better theory, because every candidate for a better theory preserves or deepens the strangeness rather than eliminating it. What you can do is sit with the precision of the result and allow it to say what it says. The universe behaves differently when observed. Observation means the creation of a fact. Between facts, reality is indefinite in a way that no classical language accurately describes. The experiment that shows this has been running for 200 years, and it shows it every time. There is a particular kind of precision that the best physics produces. Not just correctness, not just confirmation, but the precise location of what is not understood. The double-slit experiment does not leave you with a vague sense that quantum mechanics is strange. It leaves you with a specific, well-defined, experimentally confirmed gap. The universe is definite after observation and indefinite before it, in a sense that cannot be recovered by any classical mechanism. and the boundary between those two conditions is the boundary that the measurement problem attempts to locate and has not yet located. The precision of that gap is what makes the result so durable. It is not a mystery that better technology will dissolve. It is not a confusion that a clearer explanation will clarify. The experiment is clear. The explanation is absent. What is absent is a picture of what the electron is doing between the two slits in the screen that is consistent with the result and expressible in terms of something that is actually there. Copenhagen says there is nothing there to picture. Manyworld says everything is there, in all branches. Pilotwave says a specific thing is there, guided by a wave you cannot directly detect. The experiment does not choose between these answers. It only provides the question, and the question, which Thomas Young began to ask with light in 1801 and which Davison and Germer asked with electrons in 1927 and which Zeilinger and colleagues asked with molecules in 1999, and which the Bell inequality experiments answered in part in 2022, is still the question that sits at the centre of the foundations of physics. What is the electron doing when no one is looking? The answer is not in the data. The data ends at the screen, where the dot appears. What happened between the source and the screen is what the interpretations are about, and what they disagree on, and what they will continue to disagree on until someone finds a question that distinguishes between them experimentally, or until the next theoretical revision changes the terms of the argument entirely. Neither of those things has happened. Both remain possible. The experiment continues. Consider what it means for an experiment to still be asking a question after 2 centuries. Most scientific mysteries resolve, a prediction is made, an experiment is designed. The result comes in, the question closes, the field moves forward. The double-slit experiment has not worked this way. Every refinement of the experiment has sharpened the question without answering it. Every new technique for isolating quantum systems has extended the scale at which interference effects are observed without locating the boundary where they stop. Every interpretation that attempts to picture what is happening behind the data runs into a different version of the same problem. This is not a sign that physics is failing. It is a sign that the question the experiment is asking is more fundamental than most scientific questions. It is not asking about the properties of a specific particle or the behavior of a specific force. It is asking about the relationship between measurement and reality, about what exists when no measurement is occurring, about what observation, in the deeper sense, actually does to the world it observes. These are questions that sit at the boundary between physics and philosophy, not because physics cannot address them, but because addressing them requires being clear about what physics is describing and what it is not describing. The theory describes measurement outcomes. The reality between measurements is where the interpretations disagree, and disagreement between fully confirmed mathematically equivalent theories is not a problem the experiment can resolve by providing more data. It is a problem that requires either a new theoretical idea that makes a distinguishable prediction, or a philosophical clarification that dissolves the disagreement by showing it is not a disagreement about anything measurable. Neither has arrived. Both are actively being worked on. The foundations of quantum mechanics is a living field of research, populated by physicists who take the question of interpretation seriously, who develop formal frameworks for comparing interpretations, who propose experimental tests for properties that might distinguish between them at the margins, and who have not, as of the most recent literature, converged on a resolution. The experiment continues, the question is still open, and the word observation still carries inside it the entire weight of what has not been resolved. Every time someone observes something, in the technical quantum mechanical sense, a fact comes into being that was not there before. The universe becomes slightly more definite, and what it was before that fact existed, in the fraction of a second when the electron was between the source and the screen, between the emitted and the detected, between the potential and the actual, remains precisely and specifically unknown. The universe is not finished being understood, and the double slit experiment is the doorway through which any complete understanding must eventually pass. 2 slits, 1 electron, the interference pattern, the observation that destroys it, the erasure that restores it, the Nobel Prize that confirmed what was already known, the interpretations that agree on the data and disagree on the reality, the measurement problem that remains open, and the word observation, which you will never use in quite the same way again. That is all tonight had to say. What you do with it is yours.